Let's wait for some time. Maybe other people may join. Okay, I think we can start now. So this week is all about the phase diagrams and how the phase is changes with varying with the temperature. Okay, so phase in a material may undergo change as function of the temperature or pressure, are known as the phase transformation. Okay, so it is converting from one phase to other phase. In previous class, we have seen what is the different way of phase transformation occurs. I will just recap them. So here there is a different way of phase transformations. In case of in general, we have only three broadly, like gas to liquid, liquid to solid, and so on. But here we can see in the liquid to solid and further how we can classify them. So eutectic reaction where liquid converting into two solid phases, alpha plus beta, like similarly eutectite alpha one solid phase converting into two different kind of solid phases. Okay, and if it is the penetrating reaction, it is the liquid plus one solid converting into another solid, and penetratoid, it is two solids combinedly converting into another one solid. Okay, monotectic, here one liquid converting into another liquid plus solid, and monotectoid, it is one solid converting into two solids. Okay, in this case we will have a similar phase in case of alpha 2 plus another phase will be there. So it is similar to eutectoid, but here it will be the phase will be the similar, same alpha will be there plus another uh, phase alpha will be generated. Okay, and synetectic, here two liquid phases combinedly forms the one solid phase. Okay, so this is the previously we have seen, this is the iron carbon diagram. So here where is the different kind of phases, so those are transformations we can see. So here we can see above 1500 degrees and so on, the entire region will be liquid. Then after it will transform into different kind of phases. Here solid, here here solid plus liquid, here only one liquid gamma phase, and here two solid phases, gamma phase converting into alpha phase plus gamma phase. Here similarly we can see, here it is called as a,
Right.
hello.
Yes.
Yes, yeah, yeah, you were saying. Yes, yes.
Yeah, that is your doctor point, I see.
Electromin. Yes, eutectide. And so below this one, it is called as a hypoeutectide. It is above hypereutectide. Okay. So, and also we have briefly seen the what is the different welding processes. Okay, what is the welding definition? So joining of the two materials by using heat or pressure. So based on that, we have seen the different welding terminologies also. what is the weld bead, what is the parent material, weld zone, heat affected zone, and the fusion materials, and so on. Then we have see the what is the power density for the different welding processes. If in case of gas welding, we see oxy fuel. In that case, power density is less. When we go for arc welding, to resistance, laser beam, electron beam welding, power density increases. How it signifies is that if the power density is less, so the heat affected zone region will be much higher. But when the power density is much higher, in case of electron beam and laser beam, the heat affected zone will be very shorter. So that is actually desirable. But because of its cost constraints, we are not going for the laser beam and electron beam for any general applications. So we mostly go with the arc welding. And yes. So, we can see the how the microstructure looks like in the weld bead. So here in a weld bead region, we can see a columnar grace. Why columnar is that because material reaches to the molten state in a very less short amount of the time within a fraction of seconds, followed by the cooling also in a fraction of seconds. So because of the faster cooling, the grains will be not have enough time to form as a equiatomic grains. So that's why it will looks like in a columnar grains. Okay, heat affected zone is the region where it is not melted, but the region where it reaches the temperature above recrystallization temperature. Okay, suppose if it is the iron, so if I do the welding, so here temperature will be recrystallization temperature generally for iron is around 750 or like that. So in this region the temperature will be more than that, so that it will not melt, but the grains will be started c- rearranging, and grains will become coarsen. So it will become, we can see the coarse grains. And after this recrystallization, this line, this is the heat affected zone line, there will be temperature below the recrystallization temperature, so that there will be no change in the microstructure. And then we have seen the different welding processes, like so as a welding definition says, welding means whether joining by heat or pressure. So if we join by heat, it is called as a fusion welding. If we join by pressure, it is called as a solid state welding. So based on that, we have seen the different classifications. In fusion welding, we have seen the arc welding, gas welding, resistance welding, and high energy beam welding. In all of these cases, we use the heat to melt the material and uh, join them. In case of solid state welding, we are not going to melt it, but we apply the pressure and making the joining to takes place. Okay, like forge welding, diffusion welding, friction welding, and so on. Okay, this is the different welding classifications. And we have already also see the what is the in arc welding different kind of polarities. So DCN, DCEP, and AC. DCN means DC current, electrode negative. DCEP, DC current, electrode positive, and AC. So what? So whichever the positive side, that side heat generation is 2/3. So that means in DCEN case, uh, workpiece side heat generation is 2/3. So that we can see here. Very deep weld bit, and um, the less thickness of the electrode is required, because it will not going to be, because less heat will be generated there, so it will not going to be melted. But in case of DCEP case, 1/3 of heat only generated at the workpiece, so that um, the heat generation more at the electrode side. So that's why we required a bit thicker electrode. And similarly, AC, it is the 50-50 percentage. Off cycle it will be DCEP, off cycle it will be DCEN. Okay, but advantage with the DCEP is that it will gives the oxidation cleaning action uh, on the workpiece, because ions have the high mass. So once they came and hit the workpiece, so it will act as a oxidation cleaning one. So where we can require this kind of oxidation cleaning is that in case of aluminum welding, in that case we required this kind of oxidation cleaning. Okay, and we have seen the different classifications in the arc welding. So TIG welding, MIG welding, SAW and SMAW. Okay, so broadly arc weldings are o- only differs by two factors. One is the how we providing the filling material and how we providing the sealing environment. Okay, filling material in case of TIG welding, uh, the electrode is non-consumable, so we provide the filler material separately. And shielding we will provide by using inert gases like argon, helium, and so on. Okay, and in case of MIG welding, here electrode is consumable. That means whatever it is like a wire pool. It will continuously fed into the uh, molten region. Okay, and the shielding environment will be provided by uh, argon gas. Submerged arc welding, here also wire is the electrode is the consumable, but here shielding is provided by flux. Okay, flux we will pour onto the welding region. Okay, so in SMAW, here shielding is provided by flux, and welding is electrode itself the consumable, and it is a fixed length. In this MIG and SAW case, it will be a roller kind, I mean wire pool. Okay, so broadly these two are the TIG and MIG uses the inert gas, and SAW and SMAW uses the flux as a inert environment. Okay, yeah, among all these four, TIG only has the electrode not melting, because it is the we have to provide the filler material separately. Then we have seen the different kind of gas welding processes based on the how the ratio of fuel to uh, fuel to oxygen we are providing. Okay, so here in case of carburizing flame, we are having the more amount of the fuel, like 1/5 of the fuel, and 1% of the oxygen, so that there is no enough oxygen is there to completely burn the fuel, so that the flame contains the lot of unburned particles or nothing but a carbon. So where we can use this one is that surface alloying with the carbon, surface hardening, hard facing, and some alloys where it is carbon sensitivity not that much there, like nickel copper alloys and high carbon steels. Those cases we use this one. And neutral flame, where the oxygen and fuel are in the uh, proper ratio, so that the fuel will be continuously get um, completely get burned, and heat will that we heat. So this flame we can use for the any general applications like iron or any other applications. Okay, oxidizing flame, in this case we are giving the more amount of the oxygen compared to the fuel, but so because of the more amount of the oxygen is there, so we cannot use this one for the iron any steel base joining, because oxygen can immediately react with the molten pool and forms as a oxides, which is not desirable in any welding condition for the but we can use for the suitable for the copper and copper base alloys, where it is oxidation is a not a big issue. Okay, and we have also seen the different other welding processes in briefly, like friction welding, thermite welding, electron beam welding, ultrasonic, and laser welding. Okay, then we have seen the what is the different kind of phases, phase diagrams, like gaseous phases, liquid phases, and solid phases. Okay, then how the if the two components are there, how it changes, and what is the timeline, how to calculate the percentages, those we have seen. And then we have seen the iron carbon diagram. Okay, and then we have seen did the some problems. Okay, this is the what we had done in previous time. So this today we will see more about I just recapping the what is the SAR taught in the lectures only, so nothing much new into it, but we will see so how the microstructure develops. Okay, so if you see here, so if you are cooling, if we have a solution, a two elements are in the solution. So if you have one element, here is the A element, left side, completely 100%. Here B is the element, here right side, it is completely 100%. In between, it is the ratio is changing. Okay. So if I'm trying to cool it, so here at the A region, it will directly, once liquid to solid, it will yeah, once it reaches the melting point temperature, it will directly convert to from liquid to solid. But once I come to the interbetween regions, we can see here it is solid plus liquid. Why? Because so here the, if I go from here, A region can be first solidified, but B region, B element could be still in the liquid phase. So it will take some time to get solidified. So that's why it is takes the transition zone, where we can find the both solid plus liquid. Okay, so if there is solid plus liquid as there, so how the grains are actually forming. Okay, in case of microstructural point of view, how the grains will be formed. Okay, so so assume this is the enter the liquid region. So it will start with the first general microstructure, how it will looks like, it will be look like this way. So we have a multiple grains. Okay, so how the grains are actually forming is that, first if it is the liquid phase. So first once it is start temperature is lowering, so once it is reached this so in this region, so it will first forms the nucleation. Okay, nucleation is nothing but a seeds, seeds for the where the first solid phase is forming. Okay, once the nucleation is begun, actually for nucleation also there is a certain radius of the nucleation should be present, otherwise you see here is the radius and here is the Gibbs free energy. Okay, so once it is the below this radius, it is Gibbs free energy. If the particle radius is, suppose it is assume 1 micrometer, if it is the this nucleation reaches to the 0.5 micrometer or 0.7 micrometer or like that, it is high probability to again dissolve into the liquid state, because here is the Gibbs free energy lower this side, so radius is reducing side. Okay, but once we cross this critical radius, it is high probability, because it is slope is this way, so high probability it will forms as a growth, crystalline growth. Okay, so it for nucleation formation, it is necessary to any nuclei to cross this critical radius. Once it is crossed this critical radius, then only the nucleation will start and growth of the grains will be happens. Okay, once the temperature is going down and down, so this nucleation regions will be start growing, and forms as a the microstructure which we can see here. Okay, so now we can, so now I have here two microstructures. Okay, one I am having a very smaller grains, very smaller grains. So other one I am having a very coarse grains. So what could be the reason? If so, both are starting from the similar liquid state and transform to solid state. One I am seeing the very finer grains. One I am seeing the very coarser grains. What could be the reason?
Cooling rate.
Yes, cooling rate. So if the cooling rate is too fast, so the grains will be uh, become finer grains. Once the cooling rate is low, it will become the coarser, coarser grains. Okay. In other words, I am saying, so in terms of nucleation point of view, so initial stage, the all forms as a very high number of the nucleation points. Okay, but once the temperature, once if I go slower cooling, the grains will become, if there is a here, if I'm having a grain nucleation is happening here, the grain growth is happening here, here and here. If the temperature we are going at slower cooling rate, the grains will start at merge and forms as a single grain. This will start merging and become the coarser grains. But in case of finer grains, the in case of finer microstructure case, so there is no enough time to form as a coarser grains, because immediately once the nucleation form, because less time is there, so it will start getting cool down, so the grains will not get merged together, so the we can see the finer grains. Okay, this is in terms of the nucleation point of view. Okay, so here we can see how the this is called as a time temperature transition diagram. Okay, so here we can see austenitic phase above 700 degrees. This is for the iron carbon diagram. I have shown here, no? Yeah, so it is here at 700 degrees, it will be the austenite phase. So how it is transforming into the remaining perlite and ferritic phase, that is here we are seeing. So, so first we will see what is the mean by perlite, what is mean by bayonet, what is mean by martensite. and what is how the microstructure looks like. I think first we will see how those are looks like, then we can come back to here. So this is the broadly iron carbon diagram. So here is the steel and here is the cast iron. It is the 2%. So eutectic reaction, eutectoid reaction, and so on. So here is the microstructure you can see here. So pure iron, gamma phase will converting into alpha phase. How it is transforming? So it is transformed at the always any phase change happens where the lowest energy point existed. In a grains, what is the lowest energy point will be the grain boundaries. So phase transformation occurs at the grain boundary region, then it will start grow and completely it will become the alpha phase. It is for the pure iron case. Okay, gamma phase converting into the alpha phase. But in the case of if we go increase the carbon percentage, the microstructure will be bit different. So it is the ferrite, it is the pure iron that so it is the less than 0.8 percentage, it is a hypoeutectoid, and above 8 percentage it is the hypereutectoid steel, and exactly at 0.8 it is the eutectoid steel. Okay, so how it is transforming, I can show you this. Suppose if I am taking not at the pure region at the certain point, so it is the gamma phase just as in then the nucleation start at the weakest point, that is at the grain boundaries, and it will start growing ferritic phase, and it will forms the entire ferritic phase. Okay, this gamma region here, it will segregate into two phases. One is Fe3C and one is alpha. It is in a band kind of thing. Okay, it is also alpha phase, ferrite phase. It is also ferrite phase, but it is the covered with cementite phase in a laminar structure. Okay, so it is called as a parallite phase. Okay, this is the difference. In case of pure case, it will entirely will be only alpha phase, but here we will see only uh, mm, alpha plus Fe3C. This is called the paralytic phase. Okay, alpha plus uh, Fe3C called as a paralite. Okay, so it is how it look like microstructurally. We have a alpha phase and we have a black color Fe3C, because alpha phase has the very limited amount of the carbon. It can only take up to 0.02 percentage. Okay, so excessive carbon will be precipitate to Fe3C phase. Okay, next, so it is the below 0.8 percentage eutectoid point. What happens if we go above the eutectoid point? How the phase will be changes? At the eutectoid point, it will be entire region will be the parallite only. Okay, so here you can see it is at the hypoeutectoid region. So in case of gamma region, this is the ferrite forming and it is started growing, and here between the perlite is forming. So this will be the microstructure how it look like in the case of hypoeutectoid steel. Okay, till now okay, till now
Okay,
fine.
sir. Okay.
Yeah, okay, let's go further. So at the eutectoid region, that is 0.8 percentage, entire this microstructure will be formed as a parallite. So there will be no alpha phase present at all. In the case of below 0.8 percentage, we can see here some alpha phase white regions are present here. But at the in the case of at 0.8 percentage, alpha phase directly converting into paralytic form. That is, sorry, gamma phase directly converting into alpha plus Fe3C. Okay, that is called as a paralytic steel. Okay, microstructure will be looks like this one as a laminar structure with alpha phase and Fe3C. Okay, so how hyperelectric steel microstructure look like? Okay, that is after 0.8 8 percentage. Okay, how it will be look like. Okay, so similar to what we have seen previously, here we have a gamma phase. Okay, once it is reached touch this region, okay, the nucleation will start takes place at the weakest point, that is the grain boundaries. Here, instead of the we see in hypo steel case, there is the alpha phase is forming, but here we will see the Fe3C nucleation, because we are having the more carbon percentage in this region. So Fe3C will be precipitate here, and it will start growing, and in between region will be the perlite only. Perlite is nothing but alpha plus Fe3C. Okay, so only difference is that hypo and hyper is that here surrounding region in hypo case it will be the alpha phase, but here it will be the Fe3C. So how the microstructure will be looks like? So it will be paralytic phase surrounded by Fe3C. Okay, so here you can see. So up to the hypo 0.8 percentage. At the purest iron case, it will be totally alpha phase. Once it is going down, going to 0.8, the Fe3C content is increasing. Okay, it is reaches the almost the 100 percentage. After that, it is the paralytic phase. The paralytic phase, and it is at the 0.8 percentage. Okay, the Fe3C content precipitations, which is accumulated at the grain boundaries, that will started growing up to this is the 6.67 percentage. Okay, it is the 2 percentage. Here is the 2 percentage. It is the 6.67 percentage. Up to here, it will be reaches the pure Fe3C. So after that, there is no carbon intake will be takes place. So that's why iron carbon diagram will be stop at the 6.67 percentage. After that, even though how much carbon you add it, carbon will be separate, segregate out. It will be not as a Li form. Okay, so the with increasing the uh, carbon content, the paralytic percentage will be started reducing. Okay, here we cross the cast iron region above after 2 percentage, and it will be up to the 6.61 percentage. Okay, so Fe3C mostly the hard and brittle phase, so that's why once the cast iron carbon percentage increases, the cast iron become more brittle, and so okay. So this is how the phase changes with the um, with in case of steels. Okay, um, with increasing the carbon percentage. Okay, now we will see the how the phase changes by changing the temperature. Okay, because cooling rate also changes the how the microstructure looks like, right? So we will see that one. Okay, so here is a microstructure in brief view. Austenitic, ferritic. Austenitic is the gamma phase, that is FEC, FCC. It is the BCC. Perlite. Perlite is the we have a alpha plus Fe3C surrounded by sorry. Okay. Next, what is the temperature time transformation curve? Okay, this is uh, tells the how the temperature cooling rate affects the microstructure. Okay, that we can see. First is the nucleation and growth. Just we have discussed previously. The formation of the stable particle once it reaches the above the critical radius region, critical radius, then nucleation will start to happen, and then increasing the growth happens once nucleation is begin. Okay, so now we can see, yeah, nucleation. Once here is the liquid state, the nucleation started, it will start growing to form as a grains. Okay, so here is the you can see here is the nucleation rate and growth region. Okay, so at the lower temperature, lower temperature, it is the melting point, so it is the lower temperature, the nucleation rate will be much more higher. Okay, at the higher temperatures, if we holding it for much more longer time at these temperatures, the growth will be much more higher. So if you hold the your material, I mean nucleation at this temperature, which is lower than here, so because of the higher number of the nucleation rate, the finer microstructure will be there, that will not get merged together and forms a bigger grains. And here we can see a less number of nucleation, but enough time is there to form to make the those nucleation to grow bigger, so we will get the coarser grains. Okay, so here is the TTT diagram. So here we always see that this is the C kind of diagram. So here the transformation will start. This first T will represent the transformation starting phase, and it is the red C is the one which is the transformation reaches to the 99 percentage. Okay, 99 percentage of the one phase to other phase it is formed. Okay, in between it is the liquid plus alpha phase. Okay, here is the x-axis is the time and y-axis is the temperature. Okay, if I'm going very time, here is the x-axis is time now, so here is if I give very less slope, that means more time, so I can starting of the this region, starting of the nucleation is here, and it is the enough time is there, and the coarse grains will be started growing, forms as a coarser grain. But if I give the moderate cooling, so here we can see here it will come, and here it will start growing nucleations because of higher nucleation rate will be there. And so here you can see it is touching at the starting point, you can touching at the lower point. Here you can see that starting it is touching at the higher point. Okay, that is what makes the difference, you can see here. Okay, if that C curve touching at the higher point means there is a pathway for the growth is much more higher, but nucleation rate is less. Okay, so the less number of nucleus is there and more amount of the time is there, so that we will form a coarser grains. But in case of here, in case of this pink color curve, the nucleation touching rate here it is less temperature compared to this one, so here nucleation rate is much more higher and time is less. You can see x-axis point of view, it is very less, so more nucleus and less time gives the finer microstructure. Okay, so if I give the much more faster cooling, so that it is not even going to touch this C curve. Okay, that means it is not going, there is no enough time to form the alpha phase also, so then it will forms as a martensitic phase. Okay, so you understand, right, all the difference, coarser grains, finer grains, and martensitic phase.
Yes, sir. Yes, sir.
Okay, so now comes the benetic phase, where the benetic phase is coming from here. Okay, that we will see. So alternating to benetic phase, where is the benetic phase is coming, that we will see. Okay, so for benetic phase we will cool down, and after that we will hold for some time, so that it will after this is the nose point. So once we cool down, we will not touch the nose here, and it will reach here, then we will hold for some time, so that it will form reach to the B region. B region is nothing but a transfer paralytic region, then it will we will hold for some time, then it will cool down, so then it will form the benetic phase.
So what is the nose point, sir?
Nose point is the where it nucleation will start. I mean nucleation can be possible, I mean it will after this only the phase transformation will be started. Okay, So here you can see, where is it? Yeah, yeah. So it is the starting point of the phase transformation. Okay, suppose it is entirely liquid, it is have to convert it entirely into the solid phase. Okay, so it will not completely immediately transfer into solid phase, right? It will take a liquid plus solid region will be there, the transition region. Okay, so in this transition region, the nucleation will be starting takes place. That nucleation will start grow and to completely form as a solid. You understand, right? This transforming from this green line to this finish line. Okay, so here,
Then every point has a one nose point, right? Then starting stage.
yeah, yeah, starting stage also nose point is there, and here is the ending stage also nose point is there. Okay, so
Then
starting
you
stage nose
mentioned only one point only nose point there. That's
what
why
what
you mentioned, sorry. Actually, you mentioned only one point only nose point. Then each and every final curve, starting curve and final curve, both
ah
have on each point have nose point, right?
yes, nose point will be same. See, if you make a parallel line here, it will touch the same point only,
Okay.
y-axis. Okay, it is the
Okay.
starting region, it is the ending region. In between, how many c curves are there doesn't matter, because all are follow the similar y1. Okay, here is
Okay.
the x-axis is the time, y-axis is the temperature. Okay, nose curve is the representing the at what temperature, what time we have to provide to during the cooling time, so that nucleation will be takes place. Before the time, there is no enough time to nucleation to form. You understand?
Okay, sir. Okay.
Yeah. So for nucleation forming, we have seen now starting one here. You can see here. There is it. Yeah. So first nucleation has to reach to the this kind of critical radius. Okay. One for reaching this critical radius, it requires some amount of the time. To once it is started reaching here, then only it will start cool down. I mean, it will start growing nucleation. Okay, if it is the not reached to the critical radius, it will again high chance to convert dissolve into the liquid state, because it is the less energy state compared to the here this radius. So that, so it is the enough, this is the, you can say, like critical radius reaching time, required time. Okay, this is the critical radius required time to form as a critical radius. Once it is formed, it will start the nucleation growth and microstructure formation. Okay, so if this nose point do not touch it, so there is no enough time to form the nucleation also. Okay, so immediately this austenitic phase will directly cool down, form as a martensitic phase. Okay,
Okay, sir. Okay.
yes. Okay. TTD diagram, it is the reductor. See here, it is the coarser perlite, finer perlite. Coarser perlite means we have to give the higher cooling rate. Sorry, slower cooling rate. Here we have to give the faster cooling rate. How the microstructure looks like. Okay. So coarser perlite we can get by furnace cooling, because furnace cooling has a low. We can provide low cooling rate. Finer perlite we can get with the air cooling. Okay. So whatever this magnetic steel, tempered marten stick, and retained tartan stick, those we will see now. Okay. After that, we will come back to our original slides. Okay. Austenitic to magnetic steel. Okay. So what is the magnetic steel? Okay. Short needles of Fe3C embedded in the plates of ferrite. Ferrite is nothing but a alpha phase. Okay. So here is the Fe3C phase. Needles will be present. There are two bayonets are there, which is called upper bayonet, lower bayonet. Those we will see further. So for the to formation of the magnetic microstructure, first we have to avoid this nose point and we have to cool down up to this temperature. Okay, then we have to hold it isothermally for a longer duration of the time. Okay, so that it will again touches this region and forms the magnetic phase. Okay, this is called as a ash tempering. Okay, ferrite nucleation is the first step in magnetic formation. Okay, in contrast with the cementite nucleation in the perlite. Ferrite uh, ferrite plate formed by shear mechanism and martensitic formation. Okay, just let's you go. See the now as I said, there is the two different kind of magnetic phases are there. So one is the upper magnetic and second is the lower magnetic phase. Upper magnetic phase means it is the compared to this one, it is the bit higher temperature we are holding it at. Okay, so here is the you can see here, even though we can hold it at here also like that below the nose point, wherever we hold it we will get the isothermally we will get the magnetic phase. Okay, so if I hold it at above region, high temperature region, that means there is enough time is there to this mm, cementite to segregate Fe3C phase to segregate out of the alpha phase and form as a thicker plates between the alpha phase. But in case of lower baronet, because of the lower temperature, because if lower temperature means lower diffusion rate. So this Fe3C phase cannot be completely exit this alpha phase, so that they will form as a needle kind of structures inside the alpha phase also. It will form between the alpha phases and inside also. This is the difference between the both magnetic structures. Okay, so this is the how the microstructure looks like here in case of alpha phase and surrounded by Fe3C, but here lower magnetic we will see the needles of the magnetic Fe3C inside the matrix. Okay, so where we use our okay, I think that's enough point, that's enough for the introduction into this part. Okay, so now we have seen here what how we can produce this kind of paralytic phase, magnetic phase, and martensitic phase, how we can achieve it, and what is this time transfer diagram. You understand all this part, right? Yes. So next coming to the CCT diagram. It is also similar thing, just the cooling rate, just we what we have discussed it, which kind of phases forms. Like if I go for the 0.01 degree centigrade per second, it is nothing but a slower cooling rate. We can get a paralytic phase with a coarser grains. And if I go with 3 degree per minute, it so 3 degree per second, we can get a finer grains of the parallite only. Okay, here you can get the 35 degrees and 140 degrees, it will you will get the martensitic phase. And here you will get the 35 degrees, you will get the alpha phase plus gamma phase plus martensic, both phases will be there, because there is it is not completely transformed into paralytic phase. Within the this nose curve itself it is started cool down. Okay, so this is all about the lecture part in for this week. Okay, so you can see here, so we can try to do some problems based on what we have discussed till now. Okay, so in I think answers also I have kept it open. Okay, just let's discuss it what it is. Okay, in time temperature transformation diagrams, the nose represents, okay, maximum transformation temperature, minimum transformation temperature, end of the transformation, start of the melting. Okay, so maximum transformation temperature, what it will be, where is that
Parallel.
yes, to, yeah, here. Mhm. It is the maximum transformation temperature. Okay, and it is the uh, sorry, it will be the maximum transformation. It is the minimum transformation temperature. Below that, it will not be form. It will not transform into. Okay. And end of the transformation is the this finish curve, and starting of the melting, that is not, because that will be at the above portion. Here Tm is the starting of the melting point, so it will be, answer will be the B. Nose indicates the shortest time required for the transformation at the optimal temperature. Okay, next, why does rapid cooling suppresses diffusional transformation? Okay, so why rapid cooling? Rapid cooling means there is no enough time to diffuse the diffusion of the atoms, right? So once the diffusion, how it takes place, for diffusion occurs, we require two things. One is the high temperature, second is the high time. But in case of rapid cooling, we are not providing the temperature also going down, and the time is also less, so that uh, diffusion will become slow. Okay, nucleation rate increases, no, because crystal defects disappear, atomic gain energy, none of those. So B will be the answer. Rapid cooling reduce the atomic mobility, makes the diffusion too slow. Next is the, which phase transformation lead to hardest microstructure in the steel? Okay, so which phase is the always the martensitic phase, which is the fastest cooling rate, will always generate the finer microstructure and higher dislocations, and distorted crystal structures, which results the um, less diffusion of the atoms in the crystal structure, less the diffusion of the defects and so on. So paralytic means it is the proper crystal structure formed, so there will be no that much amount of the defect regions are there, which can act as a it can obstruct the moving of the dislocations. Okay, I mean, so it will be the, which is the fastest cooling rate, that will be the answer. So that will be the martensitic phase. Okay, by next, after martensitic, which one will come? Ferrite, perlite, barytite. Which one will be the hardest microstructure after martensite?
Benetton.
Peritite. What about Bennett? It is the one now which we miss the nose curve, and then we hold it for isothermally. We hold it for some time. So it is the fast next fast cooling rate, na. So that will be Bennett formation. Bennett. Okay. After Bennett phase, then Perlite will be the hardest phase, because it has the Fe3C also. After that, ferrite. Ferrite is the purest alpha phase, so it will be having the less hardness. Okay. Which transformation is controlled by both nucleation and the growth? Okay. Martensity transformation? No, because Martensity is not even touch the uh, uh, growth, so there will be no nucleation generation and no growth also. Okay. Diffusionless transformation? There is no diffusionless transformation, nothing but a without touching the nose, we are reaching below. That is a Bennetic phase also will come here. So it is and diffusional transformation. So which are the paralytic phase formation, faster cooling, moderate cooling, all furnace cooling, and air cooling? All of this comes under diffusional transformation, because there is enough time to nucleation to form and grow and diffuse into coarser grains. Okay. Magnetic transformation, that is not. So answer will be the C. Diffusion transformation process, nucleation followed by the growth, both required for the atomic diffusion. Okay. Next is the Nucleation during the phase transformation refers to. So growth of the new phase, formation of the stable embryos of the new phase, completion of the transformation, rearrangement of the atoms by shear. So what is the nucleation formation means? As we have seen here. Uh, So here nucleation formation means we have formed a embryos, nothing but a critical radius it has reached, so that we can nucleation will start grow. Okay, this is called as a nucleation initiation. I mean nucleation starting. So formation of the stable embryos, because if it is the less than the critical radius, it is not called as a nucleation formation, because that whatever the formed that solid phase, that will again dissolve into the liquid. So answer will be the B. Okay. Next is the which phase transformations occur without atomic diffusion. There is which phase atomic diffusion doesn't happens is the martensitic phase, because martensitic phase the cooling rate is much more very high, almost 140 degrees per second or like that, so that there is there is no phase transformation and so on. So austenitic will be written as a, I mean FCC phase written as FCC phase and forms as a Martinsic phase. In other words, Martinsic phase we call it as a diffusionless transformation phase. Okay. TTD diagram also known as a B isothermal transformation diagram, because we will considering the with no changing the temperature with the time. So that's why it is called as a isothermal transformation. Next, in TTD diagram, eutectoid steel, the nose of the curve represents. In eutectoid steel, maximum transformation temperature, minimum undercooling, shortest time required for the transformation, and completion of the transformation. I think it is a repeated question only. We have already seen previously here somewhere. Yeah, here. Similarly, minimum time required for the transformation. Similarly, it is just paraphrased question only. Shortest time required for the transformation. Okay. Next, which phase forms at high temperature just below the eutectoid temperature in TTT diagram. Just at higher temperature means coarser grains, less nucleation. So which will be the answer? It will be the C, because we can get the coarser grains. So there is enough time to grains to grow. So it will be the coarser grains. Okay. Next, benetic formation occurs in which temperature range? Okay. Above the perlatic region, between the perlatic and martensitic region, below the martensitic starting point, only eutectoid temperature. No? Above perlatic region, it will be found the perlatic phase. Between the perlatic and martensitic region, then there it will be found the benetic phase. And below martensitic starting temperature, it will be the only martensitic phase only. Then eutectoid temperature, that is not. Okay. So answer will be the B. Next, the martenstate starting temperature indicates first completion of the martensitic transformation. No, because martensitic transformation never completed. It is with because it is diffusionless transformation, so it will never complete. Beginning of the diffusional transformation, it is diffusionless transformation, so there is no point of diffusion transformation. Temperature at which martensite began to form, okay, that is the and temperature of eutectoid reaction. No, so answer will be the C. Martensitic temperature where martensite start forming during the rapid cooling. Next, which transformation in the steel is the diffusionless? So obviously diffusionless is the nothing but martensitic transformation. Next, compared to TTT diagram and CTT diagram, source. Okay, what is the difference is, in other words, what is the difference between both of them? Okay, faster transformation, low critical temperatures, transformation during the continuous cooling and equilibrium phase only. Okay, so CCT diagram describes the transformation during the continuous cooling, which closely relate to the industry cooling conditions. Okay, it is nothing but here you can see the difference. So it is the TTT diagram. It will say which phase will form at which temperature, how to form it, and it will say it is the CCT diagram. It is the same thing, but showing the cooling rates. So here we can get the grains, finer coarser perlite, finer perlite, uh, gamma plus martensite and martensite phase, and so on. Okay, yeah. Next question: why transformation curves in CCT diagram shift to right compared to the TTT diagram? To increase the nucleation rate, reduction in the reduced diffusion during the cooling, higher carbon content, and presence of the martensite. Okay. Yes. So it will be during the continuous cooling, material spends less time at the each temperature, so that the transformation requires longer. Uh, I have to look into this question. For the same steel, which cooling condition is more likely to form martensitic? Slow furnace cooling? No. In this case, we will form the coarser perlite. Air cooling, finer perlite. Continuous slow cooling. It is also maybe in between. Rapid quenching. Rapid quenching will produce the martensitic phase. Eutectide steel is a quencher from the austenitic region to a temperature just above the martensitic and held isothermally for a long time, and final microstructure will be. So it will be Benetic phase, because as we see, for formation of the Benetic phase, we will avoid the nose, and there above the martensitic starting temperature, we will hold for isothermally, we will hold for a certain duration, then it forms the Benetic phase. If it is just above the martensitic transformation one, it is called as a lower Benetic phase, and if it is a bit higher temperature holding, it is called as the higher Benetic phase. Two ideal eutectoid steels samples are cooled from the austenitic region. Sample 1 follows the TTT path and sample 2 follows the CCT path with the same minimum cooling rate. Which statement is the correct? Both will form the identical microstructure. Martensitic form more easily in the TTT. Diffusion transformation are more suspended in CCT. Perlite starts earlier in CCT than the TTT than the CCT. Why? Because TTT diagram, it will shift bit towards the left side, so that during the cooling curve it will first touch the TTT diagram, so that it will be the answer D. A steel just misses the nose of the TTT diagram during the cooling, most likely microstructure. Martensitic only, even if whatever the, if we miss the nose means it will forms the martensitic only. But if you in between, if you hold it isothermally for a certain duration, then it will forms the Benetic phase. Otherwise, it will be martensitic phase only. Which statement regarding the Bennet formation is true? Bennet forms purely diffusionless transformation. No. So there is just some diffusion will be there. The Fe3C phase out of the alpha phase. So it is not only diffusionless transformation, with the martensitic phase. Okay. Upper benetic forms at lower temperature than the lower benetic. No, because upper benetic means it is a bit higher temperature than the lower benetic one. See, benetic has the mechanical properties intermediate between the perlite and martensite. Yes, because perlite is the bit relatively softer and less hard. Martensitic is harder and brittle, so benetic will be in between. Benetic cannot form a ductile steel. No, that is not. So answer will be the C. For a given steel, martensitic temperature will be increases with the increasing carbon content, decreases with the increasing carbohydrate rate, be independent of the composition, and equal eutectoid temperature. So higher carbon stabilized in the arsenate, then lower the martensitic temperature. So answer will be the decreases with the increase in the carbon content. In CCT diagram, a slow cooling rate generally results in. So what it will formation of the slower cooling rate, nothing but there is enough time to nucleation form and growth, so nothing but a coarser grains, formation of the coarser microstructure. A steel sample is quenched to temperature between benetic and martensitic and held isothermally, which transformation sequence is most likely. So above martensity transformation, wherever we hold it isothermally, it will forms the benetic phase only. So if it is above that, it will if just above the martensitic line means it will be the lower uh, benetic phase. Which of the following microstructure requires the faster cooling rate to obtain? So fastest cooling rate nothing but a D martensite, because which is where we have to avoid the nose, and it is the diffusionless transformation. Why does martensitic formation not appear on the TTT C curve? Because answer option A, it occurs too slowly. No, it occurs very fastly. It requires nucleation and growth. No, because it is not even touching that C curve. It is a diffusionless and time independent transformation. Yes, because once it is touch the martensitic starting point, how much time you hold it, it will not going to change. It will not going to diffuse anything, because the martensitic starting temperature itself 150 degrees are like that. So their diffusion is much more less. So nothing but diffusion less. So that doesn't that other words, even though how much time you hold it, there will be no transformation. That is the time independent. So answer will be the C. It occurs only at the high temperature. No, that is also not. A steel cooled continuously forms the Bennett in CCT diagram, but not corresponding TTT diagram. The most likely reason: faster nucleation during the continuous cooling, lower martensitic temperature, different cooling path through temperatures and time. So only possible is that this different the pathway decides the which kind of phase it will be forming. So it will be the answer will be the C. Fine perlite forms instead of coarse perlite because high faster cool bit faster cooling rate. So higher diffusion rate, no, higher diffusion means nothing but a higher temperature. That is not low transformation temperature. Yes, because of the low temperatures, there is no enough diffusion takes place. See slower cooling rate, no slower cooling rate, nothing but a higher temperatures and a higher diffusion rate. D, higher martensitic temperature. It is nothing to do with the martensitic temperature. Okay. Which sequence correctly represents the increasing in cooling rate? Okay. Cursor perlite, finer perlite, Bennett, and martensite. Yes, that will be here next. Martensite, Bennett, perlite, ferrite. Order is correct, but arrows are different because first it will comes the ferrite, then perlite, then Bennett, and then martensite. Bennett, next C option, Bennett, martensite, perlite, and ferrite. No, because martensite should be comes at the last. And ferrite, perlite, martensite, and Bennett. No. So answer will be A. I think that's it from my side. Is there is today class is fine or anything to discuss further?
So pro-eutectide steel, pro-eutectide alpha ferrite, you didn't discuss that one. What is that
Pro
one?
you take right. Just I have discussed na. Just a moment, I will show you. So here before here na hyperotectide. Okay, here it will forms the first alpha phase, then between the paralytic phase will be there. After this here exactly this point it will be completely perlite. After this first the Fe3C will be segregate at the grain boundaries, then the perlite will be formed. That we have discussed na. Here is that one.
That one only we discussed, sir, not about
Okay,
pro-eutectide
after
ferrite.
that cast iron, those are cast iron part. I didn't go into that one. Okay, because m- most of the know that I'm not aware of that, but I mean not into. So yeah, this part only below before the 2% of that one. Okay, that I think I have briefly introduced. Now, wait, just I will show you. Here is it. Mhm. Yeah, here. You can see here. So up to 0.8 percentage, alpha phase will be started decreasing, palette phase will be started increasing. After 0.8 percentage, Fe3C phase will be started increasing, palette phase will be started decreasing up to the 6.67 percentage. So up to 2 percentage we call it as a steel. Similar trend will be follow. Similar microstructure changes will be follow. But amount ratio of the Fe3C to perlite will be changes. See here, here what are the phase transformation here? Where is it? Yeah, here happening. Similar trend will be follow. First Fe3C will precipitate in the perlitic phase. Only difference will be the ratio of these regions. So you can see here. Is it cleared your? I mean, your doubt or?
Okay, sir. In after means after eutectide steel only, pro-eutectide steel will form, right? This one
Ye-
after
yes, yes,
0.8% carbon. That is
yes.
called.
After 0.8 only, it will forms the
Okay, okay,
perlite and
okay.
Fe3C. At exactly 0.8, it will be formed as a perlitic. So here is you can see hypereutectide. It is the 0.8 percentage. Up to 0.8, we will see the ferrite plus perlite. After 0.8, we will see the perlite plus cementite.
Sir, in cooling curve, sir, TTT curve, sir, A3 line is not touching, right, sir? Actually, they given question on that one. It is not related to, sir didn't explain that one.
Which in cooling curve?
In, yeah,
Just a
yeah.
moment, I will go there. So here is the yeah, here is the cooling curve. Yes.
They asked in question, sir. Actually, A3 line is not touching like that. It is not touching, right? Only A1 line will touch, right, sir?
Yeah,
For
yeah,
cooling.
yeah, yeah. Got it, got it. What you trying to say is I understood. Just a moment. No, not this one. Week two. Yes. Yeah, here na.
Yes, sir.
Yeah. So here is the nose. Okay. If it is not touching the nose and if it is continuously cooling means which case it will form
Martin.
martensite. Okay. If it is here, it is partially touching, but it is not crossing the finishing point. Okay.
Sir, sorry. Sir, sorry. Actually, they are in assignment question they given, sir. A1, A2, A3 they been given, sir. What is the
Okay.
A3? A3 it is not touching. It is
Okay.
if it
Okay.
is
Actually, yeah, I didn't see that assignment questions, so I don't know that.
that's why sir
Yeah, but
explain in
most
that.
probably that is belongs to this among the one curve. They represent the A1, A2, A3 like that only. Maybe
Oh, in phase diagram they mentioned right A1 A1 line it is lower critical temperature like that. Same I think that one. That's why I have doubt.
okay, okay.
Which one that
So
one? A1 in cooling curves one line is there and upper the high temperature one line is there
okay,
and
okay.
middle
Here is
one.
the A1. Okay, A1 is the melting. Here is the austenitic phase. Above A1 line, you will find only austenitic phase. How much the cooling
Yeah.
rate it will be?
Yes. Yes.
Yeah, because above that region, only austenitic phase only you will find it.
Means it means A3 line is not touching the cooling curve. TTT diagram or CCT.
Where is A3?
A means just phase diagram just showed me, sir. It is in gamma phase for 90 degrees to it is coming under 0.8 percentage of ectotite shield, right? That is mentioned as A3 in phase diagram.
900 to how much?
So it is coming cooling down to the 0.8 percentage of ectotite point.
Okay, okay. I'm not sure about it. I think I have to see.
That's why I have the doubt. Sir didn't explain that one, but that question is coming in assignment.
Okay, okay. Or you can share that one, na? So maybe I can see. You can share Google in this Google Meet. Maybe I am or other people also may see. Possible for you?
Actually, that question I didn't still now I didn't
Okay, now you
see
are
that
not
one.
having. That's okay.
Yeah, that's why I have
Okay,
doubts. That's why tell that
okay,
one.
okay. Okay. Okay, I will
So
get back to
can
that.
we how can
But
we this
huh?
recording this season recording we can get?
Sure. I will upload in the YouTube and I will share that link also. In that NPTEL people will share you.
Sir, okay, upload sir please.
Yes, yeah, sure.
Thank you sir.
Yeah,
Thank you very
sure.
much for
Okay.
I got so many doubts in this one, but all are clear now. Thank you.
Okay. 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 So,
Thank you.
okay. Anything to discuss so far today?
Sir, I have one request for you, sir.
Yeah, sure. Please.
Actually, gave, if we solve more numericals, then it will be helpful for us for the examination.
Okay.
Instead
Okay.
of discussing about the theory,
Okay. Next.
if we concentrate on more numericals,
Yeah. Next class onwards, I will bring more numerical questions.
After
oh,
we will any descriptive mode question sir
What? This?
in exam
No,
in
no. I
final
think
exam.
all are will be the multiple choice questions are like that only. No descriptive anything.
we are getting out of the syllabus which are explained in those.
Okay, actually, I'm not that much aware about it. How the examination will
Okay.
be conducted. Up to my knowledge, it will be. My assumption will be it will be the multiple choice questions only, because if whatever they are giving as a assignment, that only will be similar format only they will follow. But you can confirm once with that NPTEL people. You can just write down the mail regarding the examination pattern. They will clarify you about that.
Okay, sir. Okay.
Yes. Okay. So if you want to leave, you can leave. I will be here for another some 10 minutes, because here I have to spend around 140 hour, 145 hour like that. Yeah.
Sir, can we discuss about one question regarding the high
Yeah, sure.
carbon content?
Yeah, sure, sure. Yes. Which one? High
Uh,
carbon content.
just yes. Whenever the carbon content increases, the
Okay.
arsenite.
Okay, here, yeah. Yeah, this is the carbon content. Oh, that question. In multiple choice questions you are talking about.
Yes, yes, yes.
In multiple choice. Okay. So actually, I couldn't able to find it, but I can explain it. So carbon content, if is increasing, the carbon will try to retain the austenitic phase. It will not to try to form the martensitic phase early. Okay, so if carbon content is high, means the martensitic transformation will be lower, because it will try to retain the austenitic phase only. So what is the martensitic phase? It is converting from alpha phase, that GABA austenitic phase, to martensitic phase, right? So the carbon content will try to stay in the austenitic phase only. You understand what I'm trying to say?
How it reduces the martensitic temperature,
Yes, yes.
starting
So,
temperature?
so yeah, just let me explain it in another way. Um, so first let's go to cooling curve, where maybe we can explain it well. So, where is it? Yeah. So, so consider here is the 200 is the martensitic formation starting. Okay, in general alpha phase. Okay, here about the 200 it will be in gamma phase only. Below it will be the martensitic phase. Okay, so yeah, I have another alloy which is having the high carbon content. Okay, if I increase the carbon content, what it will carbon try to do is that carbon do not like to be in the martensitic phase. It like to be mostly in the austenitic phase. Okay, so because it will try to be in the austenitic phase, but temperature is going down, so it is nothing but like stabilizer. Carbon is a try to keep it retain in the austenitic phase. Okay, if it is trying to retaining in the austenitic phase, means to convert into the martensitic phase, we have to reduce the temperature lower and lower. Sometimes we may cross the room temperature also to form the Martinez phase. Are you getting what I'm trying to say?
I got it. I got it. Thank you.
Okay, yeah, because the carbon is a try to keep the austenitic phase only. Okay, it do not like to form immediately to the martensitic phase. If the carbon is increasing, it will much more try to retain in the austenitic phase. Okay, so martensitic phase only forms when we are lowering the temperature. So it is trying to retain in the austenitic phase means we have to further lower the temperature to forms the martensitic phase. So that's why it lowers the martensitic temperature. Okay.
Okay, sir. Thank you.
Yeah, that's so I'll be here for next 10 minutes only in this meeting. So meanwhile, if you have any doubts, we can discuss also. Meeting going on.